Welcome everyone, my name is Andrea Forman-Nékis and I will be the moderator today. Dear reporter, please start your presentation.
Good morning, ladies and gentlemen. My name is Balázs Csoma and I'm here to present problem 1 on behalf of Hungarian Team Red. First, I would like to start with the interpretation of the problem. The task can be broken down into 3 criteria that our solution must meet. First, we have to synthesize a compound comprising as many elements as possible. It must be obtained in pure form, and its chemical structure must be determinable via physical methods. And as elements would be quite difficult to incorporate into a single compound in their elemental form, it makes great sense to package them into molecules first, which will be easier to handle later. And one very elegant way to do that is by encapsulation with fullerene cages. There are many elements that can form these so-called endohedral fullerenes, and these include the F-block elements, noble gases, S-block elements, and some transition metals. However, the majority of transition metals doesn't fit inside the cage, but fortunately they can be trapped in other cage compounds, namely stannepherine and plumbosferine. And according to literature, stannepherine can host any D metal, and plumbosferine can host group 3 elements, namely boron, aluminium, gallium, indium, and thallium. Moving on to the P block, there are many amino acid derivatives that has P block elements in it, and they are available from commercial sources. These elements include silicon, phosphorus, arsenic, selenium, and tellurium. And also there are halogenated amino acid derivatives that are also available from commercial sources. And moving on to the rest of the P block, namely germanium, antimony, and bismuth, and they can form these porphyrin complexes, as you can see on the slide. And if we look at the periodic table, first we have to eliminate all the fast decaying radioactive elements because they would ruin both the chemical structure of our compound and also the purity of it. And mendelevium is one of these elements, which is, in my opinion, is pretty ironic. And the rest of the periodic table can be grouped into the previously mentioned categories. So we have the elements with the endohedral fullerenes, the endohedral stannepherines, plumbosferines, the halogenated amino acids, the amino acid derivatives, and our porphyrin complexes. Altogether, there are 87 elements which we intend to put into a single compound. The synthesis of the compound starts with the preparation of monomer A, and you can see the structure of it on the slide. It has 2 fullerene cages at the 2 ends, and those fullerene cages are doped with the same elements. And as we had 40 different endohedral fullerenes, and we want to use also an empty fullerene cage, it will give us 41 different variety of monomer A, depending on what is the doping element inside the cages. And also, monomer A has an R substituent. Take notice of that, it will be important later. Also, we have another molecule called monomer B, which has this structure, as you can see it on the slide, with a rigid stand and 2 biscalic serines at the 2 sides, and these biscalic serine rings can complex fullerenes to form strong supramolecular complex. And if we mix monomer B and monomer A together in a toluene solution, it will form a polymer, as you can see on the schematic representation on the slide. And now jumping back to the R substituent of monomer A, a specific substituent will be ordered to a given variation of monomer A, and the substituents can be grouped into these 3 categories. So we have the porphyrin complexes, the amino acid derivatives, and the third category is the same biscalic serine complex that we bisphosphorine that we used before, because they can complex standard pherines and plumbosphorines analogously to fullerenes due to their comparable size and high degree of delocalization. So now we just have to assemble our polymer. And it starts with a photocleavable resin-bound linker, which is loaded with a calixarin socket. First we have to add monomer A to it into the resin in toluene solution, then wash the plate with toluene, then we add monomer B, and again wash the plate with toluene, and we will repeat this cycle 41 times. Remember we had 41 different types of monomer A. And at the end we add C60 to terminate the chain, and wash again the plate with toluene, and just photocleaving the linker you can separate the polymers quite easily from the resin. You can elute the polymer using toluene. And after that, the polymer can be recovered from this toluene solution by a solvent evaporation under nitrogen atmosphere. About the chemical structure determination, X-ray crystallography can be used for that. And the last thing that we have to talk about is the purity of a compound. And this is ensured by the three things listed on the slide. So HPLC purification of monomers prior to the polymer assembly. It's very important to use as pure monomers as possible if you want to get a pure polymer after that. Also we have mild assembly conditions. You basically just mix the toluene solution in a moderate temperature, and that ensures that there are no cellular side reactions going on. And also the low linker density of the resin ought to help the purity of the compound.
1 minute left.
In conclusion, I would like to state that I have solved the problem as I proposed a synthesis of a compound comprising of 87 different elements from the periodic table. The synthesis should result in a high purity compound, and also its chemical structure, both chemical and physical structure, can be determined by X-ray crystallography, which is in fact a physical method. Thank you for your attention.
Thank you very much. Now the opponent has 1 minute to prepare. Dear opponent, your time is up. Please start your monologue.
Good afternoon, everyone. Today it's my pleasure to give a position on this presentation about problem 1 of the periodic table. So the presentation was both interesting and insightful, I have to admit, and I also congratulate on that. However, there were many important details which were glossed over or outright omitted. We started with the interpretation of the problem, which was absolutely correct. However, I didn't reflect whether you incorporated really as many elements as possible or just as many as you could. Moving on to the type of incorporation of the elements, the modified amino acids are a very interesting idea. However, some of them are quite reactive, namely the selenol and tellurium analogues, which contain the hydrogen selenium and hydrogen tellurium bonds, which are prone to the oxidation and electrophilic attack. You also said you cannot include the radioactive elements for the reason that it destroys your structure due to decay. However, you did include some radioactive element in your molecule. Would you mind saying how did you choose those ones and why do you think those are appropriate to be included in the molecule? As we go on with the presentation onto page 10, you mentioned the calixarin complexation and other types of complexation as well throughout the presentation. However, you fail to mention any stability constants and whether these complexations are kinetically or thermodynamically reversible. Would the synthesis of your complex allow for the dissociation of monomers during the procedure? As you went on to describe the solid state synthesis of the oligomer, you use photocleavage to disconnect your molecule from the solid state resin. However, there are several heavy atoms in your molecule which are prone to absorb photons. For example, carbon iodine, carbon bromine, or carbon selenium and carbon tellurium bonds can be quite unstable under the action of light. Furthermore, you designed an experimental procedure to synthesize the actual molecule, but you failed to demonstrate that it is actually possible. For example, solubility of the monomers, which contain a number of hydrophilic groups and quite appreciable in their size. They might be insoluble in toluene, and their solubility in toluene might not be that different from the resin, from which you absolutely need to separate them, otherwise you wouldn't get a stable molecule. Furthermore, you didn't mention any of the activations you used for the addition of the monomers in this reaction. I mean, even if you use stirring, then it might induce shearing forces in your solution which can tear the macromolecules apart, because as judged by the eye, they are quite rigid and quite sensitive to bending, for example. Furthermore, in your final molecule, there were a number of acidic moieties. For example, the sulfur-containing sulfonic acid, if I remember correctly, which might react with the tin and lead, which are prone to be dissolved in aqueous acids, for example. However, I think that once these questions are answered, your solution might actually fulfill the requirements of the problem. Absolutely. I'm waiting for your response.
Thank you. Now the reporter has 4 minutes to reply.
Thank you. First, I would like to thank you for your questions, because yes, these are very important parts of the solution. So I would like to start with your first question. So you mentioned that I incorporated many radioactive elements into the compounds, but I said that I don't want to use radioactive elements. And what I said exactly was that I won't use radioactive elements that are fast decaying. So I chose elements that has a half-life longer than 2000 years. I thought that this long time should be sufficient. So moving on to the question, your question about selenocysteine and tellurocystine. These are stable under physiological conditions. Actually, selenocysteine isn't a modified amino acid, it is an amino acid in itself, existing in nature, and tellurocystine can be incorporated into proteins under physiological conditions. So there were experiments where they tested this. You also asked about the stability of the supramolecular complex, and so the stability constant is 4.8 at room temperature, and this complex is held together by the complementary shape and the pi-pi interactions. However, it's 4.8 at room temperature, but it can be increased by just simply cooling the solution. Also, you asked about light damage, whether light can damage our compound or not when we cleave the linker. And my answer for that is that I think we can apply the light quite precisely in form of a laser or some sort when you only shine the light on when you focus the light only on the linker and not to other parts of the compound. Also, you have asked about the solubility of the polymer. I'm sorry, I just have to, and the monomers in general. And as you can see, they have very long hydrocarbon chains attached to them, and the reason why they have these long hydrocarbon chains is to make the molecule more soluble in toluene. So that's the reason why they have that. Also, you asked about what type of activation do I wish to use during the polymer assembly, and for that my answer is that nothing special is necessary to use because the reaction can be carried out at room temperature just by simply mixing the two compounds together. However, we should do the reaction at 10 degrees Celsius. It's lower than room temperature to increase the stability of the polymer. And yes, these subpolymer complexes are reversible, so they can dissociate, of course, and therefore we wish to use this lowered temperature just to increase the stability even more.
Is the discussion already?
Thank you for your answers. They were interesting, although not completely exhaustive to my questions. So you mentioned that as a reply to my question concerning the radioactivity, that you would you would draw a line of 2,000 years. However, you didn't explain why did you choose this exact number, and you glossed over the question whether this is the actual limit of our ability to incorporate elements from the periodic table, whether elements with shorter half-life cannot be physically incorporated into a molecule like that, or was it just a limitation of your solution?
Okay, now I try to get back to the periodic table slide. So, just a moment. There are many more F-block elements that could be incorporated even in the same polymer, because some of them have these endoheterofullerene complexes. But under these conditions that the task stated, that it should be pure, and so I think that under these conditions, with these limitations, I think it's really the upper limit of what elements can be incorporated into a compound, the single compound.
Thank you. Regarding my question on the photocleavage, you said that you would focus the light so precisely that you only are targeting a single bond. Even if we ignore the physical possibility of that happening, we can't deny the fact that due to the conservation of spin, any light absorbed will be re-emitted as the molecule relaxes from the excited state to the relaxed state, to the ground state, I mean. So, would the extra photon, again, break any bond in your molecule?
Well, first, the re-emitted photon ought to have lower energy than the one that we use to break the bond. And second, our polymer has a very high degree of delocalization in it, like because of, I just move one slide so you can see. So we have both the fullerenes and also in the sand there is a very high degree of delocalization, I'm sorry. And this makes our compound fluorescent. And I think that's by...
Okay, I get that.
Okay.
If you don't mind. Because you also mentioned that cysteine is stable under physiological conditions, which is undeniably true. However, even cysteine is usually happens to form dicysteine, so it dimerizes. Would dimerization in your molecule destroy the structure you've shown us?
Prior to the polymer assembly, it can't really, because we will purify our monomers using HPLC. And after the polymerization, they are just sterically cannot get enough close to each other, or it's really not likely.
Thank you. Regarding the stability of the carboxylic complex, you said the stability constant is about 4.8, if I recall correctly, which is not bad. However, if we consider the number of complexations your molecule has, it is undeniably likely that at least one of them will dissociate. So I mean, if you have a complexation constant of 5, then out of 6 molecules, 5 will be bound and 1 will be free, floating around freely. If you increase the number of monomers, then it is increasingly likely that at least one of the monomers will break from the complexation cage if my calculations are correct. So wouldn't this make the formation of your molecule actually quite unlikely, and even if it formed, making it prone to dissociate?
So,
this is the last question.
So yes, obviously the polymer isn't 100% pure. It's impossible, that I admit. However, I think that the purity should be high enough still using these conditions. And if you remember that 4.8 for the complex stability it was measured at room temperature, and we lowered it to around 10 degrees Celsius, which we should increase it greatly.
Thank you, and now it's time for the reviewer. You have 3 minutes.
Dear jury, fellow participants, my name is Marcel Bogner, and I'm going to be the reviewer of this section. Starting off with the presentational style of the performance, the slides were aesthetically pleasing, a band of informative and original illustrations, following a logical order which made the understanding as easy as possible. The reporter spoke fluently and clearly, maintaining a steady pace provided an entertaining speech. Moving on to the scientific part of the solution, in my opinion, he sufficiently fulfilled all the requirements of the task. Using mainly fullerenes and other chemical cages, he was able to include 87 elements in this hypothetical compound, which is truly impressive. During the polymer assembly, he evaluated with the several important factors as yield and purity, and as a little summary, I'd like to point out that the steps of the synthesis were scientifically backed and well described. On the opponent's monologue, he shone deep understanding on the topic, stating numerous relevant questions regarding the insights of stability and solubility of the compounds, just to highlight a few of his points. During the reporter's monologue, the reporter addressed the questions, including supplementary slides, mostly answering them with a throughout the description. Moving on to the discussion, the opponent emphasized his further concerns regarding steps of photo cleavage, which could be a weak point of the solution. As a conclusion, I reckon that both participants testified their deep knowledge on the topic, providing an interesting and civilized debate. Thank you.
Thank you very much. Now it's time for the jury's questions. Jury, who has a question? Answer, please.
Good. So my question is to the reporter. You mentioned that to determine the chemical structure of your molecule, you would use X-ray crystallography. My question is that what information does this method provide, and how would you use this information to analyze the chemical structure of your molecule?
So, may I go through my appropriate appendix? So, we want to use a single crystal X-ray diffraction, which can be used to provide information about both the bond lengths and both bond angles, and from this we can build up our polymer. So that's my answer for that.
Danish?
Okay, so I would like to comment on your solution that it's an impressive plan and layout for the synthesis of your compound, but it contains a vast number of steps, which means that the yields will be diminishing over the synthesis. So what do you think the overall yield would be for such a reaction, and for the individual steps as well?
Well, I don't have an exact estimate for what the yield is. However, I can say that it's extremely low. That's for sure. Even preparing our endohedral fullerenes, the yield for them is between 0.01 to 0.001%. So yes, it's an extremely inefficient process. However, we don't want to use this polymer for basically anything. So synthesizing it into so it's not really important to have an efficient synthesis for it. So therefore, the low yields shouldn't pose a problem.
Okay, so my question would be also to the reporter. So, to me it seems that you tried to encapsulate as many elements as you could in fullerene. So why couldn't you encapsulate the others? What determines the ability to be encapsulated in fullerene?
Well, the main factor which determines which can be encapsulated into fullerene and which can't is the size of the doping atom, and that's the reason why most transition metals just simply doesn't fit inside the cage. But more specifically, I only used those fullerenes that have been made already and was described like their synthetic procedure in literature. So maybe theoretically there are other elements that can be encapsulated into fullerenes, but I only wanted to use those that are for sure exist.
Next question, Athena.
Okay, so I would like to have a second question to the reporter. So between your monomers there are only secondary bonds and interactions. So how could your compound or your solution still be classified as a compound? What is your definition of a compound?
So yes, our polymer isn't a molecule, but it's a compound. Because the definition of a compound, as you can see it on the slide, that compounds are composed of atoms or one or more than one kind of element in some form of chemical combination between the atoms. And a compound may be molecular or ionic or both. A compound is a single chemical substance. So basically anything that contains at least two atoms that are bound together can be called a compound.
Thank you very much. Now it's time for the general discussion. Who has a question?
So my question would also be regarding the stability of this compound. So you're using several exotic compounds, for example, the endohedral noble gas fullerenes, or these complexes. And my question would be if you have any data that these very different compounds are stable at a given under given conditions. So you had a exact parameter where all these monomers would exist. Since, as I'm sure you know, for example, they are obtaining these noble gas complexes under the extreme pressure of 3000 bars. Yeah, that would be it.
The endohedral fullerenes that contain the noble gases are created by simply evaporating carbon using either arc discharge or laser ablation, and then the fullerene cages will form in the gas phase. And the reason why you need to use that pressure is to basically make the gas phase more dense in terms of noble gases. So the chance of encapsulating a noble gas atom inside these cages will increase, and therefore the yield will be a bit better. But all the compounds that are used are stable in both at room temperature and at 10 degrees Celsius, which be used for the polymer assembly.
Okay, so I have a question for the opponent. So what do you think, what's the weakest point in this solution from a scientific point of view?
Thank you for asking that. I was just about to highlight that the stability constants and somewhere lack thereof means that the complex will not be stable as such, as due to the entropy the monomers will dissociate eventually, even if the bonds as one are stable. The total of the complexation bonds, the Kelly-Serine complexations, are not stable as a whole. That's it.
May I give an answer to that? So the structure of this polymer is from literature. It's from an article in which they were able to form quite long fibers of this polymer. Actually, they could, as I remember, they could take out from the solution in the form of a string. So although these complexes doesn't seem to be stable, they are stable, as they could form like quite a long polymer from it in the article.
Any other questions?
Yeah, so I would like to ask a follow-up question in terms of the yield. So while your response seemed a sufficient one, I would like to point out one of the main criteria of the exercise that you need to be able to determine is structure by physical methods. And in order to do that, you need to produce appreciable amounts of the compound. So that way, the yield should be a concern. How would you like to tackle that issue?
Well, my answer to this question is that really only the polymer the yield of the polymer assembly is the one that matters, because you can prepare the monomers prior, so only the assembly of the polymer is the one that in this case is important, and the number of polymer, so the amount of polymer that you will form is just depend on how much linker do you have on the resin, so you can quite easily synthesize a given amount of it, so the yield shouldn't be a problem.
Okay, thank you everyone. This is the end of the general discussion. Dear jury members, please write down the grades. Are you ready now?
Yes.
Grades for the scientific part of the report. Please show your grades. 5, 5 and 5. Thank you. Grades for the presentational part of the report. 5 minus, 5 and 5 minus. Grades for the opponent. 5, 5 plus, 5. And grades for the reviewer. 5 plus, 5 minus and 5. Thank you. We have a 5 plus for the opponent from Danish. Please explain your mark.
Okay, so I would just like to congratulate the opponent for the sheer amount of work and just dedication put into the exercise, because he clearly demonstrated that he understood the theoretical background quite well and asked numerous questions. So many that I couldn't feel otherwise but to give a 5 plus for this wonderful performance. Thank you.
Okay, and we have a 5 plus for the review from Ati. Please explain.
Okay, so dear reviewer, your task was to summarize and evaluate the reporter, the opponent, and the scientific debate. And you fulfilled all the 3 tasks really perfectly, and basically that's why I give you a 5 plus.
Thank you. Thank you everyone. This is the end of the first round.